In this video, we are going to talk about the Markovnikov and then the anti-Markovnikov's rule. Let's consider this reaction. If you add HBr to this alkene, what will be the product? What will happen is that the HBr will get substituted across the alkene, and therefore the product we are going to form is this product. Now, what if this product was a propene? Here was a butene, and we add HBr. You see that in this case, there are two molecules that we can form. So comparing these two products, which of these two products will be the major product? You see that this product will be the major product, and then this one will be the minor product. So this major product obeys what is called the Markovnikov's rule, and then this minor product obeys a rule that is called the anti-Markovnikov's rule. It is also called the Kharass effect, or another name it is also called is the peroxide effect. Now, there is a little addition to the formation of this molecule. So when we come to the the Kharass effect, I will explain more, because the starting reagents, we need to add something more to it. So let's look at the mechanism that leads to the formation of the Markovnikov's product. So this is the starting material that we're given. We're given one propene, and then we are adding HBr. So what will happen is that because this alkene has these pi electrons, it makes it nucleophilic. And remember that this is hydrogen bromide. Bromine is more electronegative than this proton here. So the bromine pulls the electrons shared between it and the proton more towards the side, and therefore it has partial negative and partial positive polars on it. And therefore bromine will assume partial negative charge, and then the proton will assume a partial positive charge. And because of this partial positive charge, it makes this proton electrophilic. And because of this pi electrons, it makes this propene nucleophilic. So the nucleophile will donate a pair of electrons to this proton, whilst causing this bromine to cleave off. So in the next step, what will happen is we'll create an intermediate, which is a secondary carbonium. So this is the proton is here. So we'll create this intermediate, which is this carbonium ion intermediate. Now you can see that there are two ways in which this carbonium ion could be created. Apart from here, the electrons could also be donated by this carbon, and therefore the carbonium ion could also be created like this. So the proton could be here, and then the carbonium ion could be created here. Now, we know that this is the one that will lead to the formation of the major product. But now, why? You see that this is a secondary carbocation, and this is a primary carbocation. A secondary carbocation is more stable than a primary carbocation, because the metal here donates electrons into the center through inductive effect. So it makes this carbocation more stable than this one, and therefore this one will lead to the formation of the major product. So in the next step, the bromide that was cleaved off will come and donate its pair of electrons into that center, and that's what will lead us to the formation of the major product, which is also known as the Markovnikov's product. Markovnikov's reaction can happen with any of the halogens. So it can happen with HI, which is hydrogen iodide. Can also happen with hydrogen bromide, hydrogen chloride, and also hydrogen fluoride. In terms of increasing order of reactivity, then it will be going in this direction. And the reason is because you know that iodine is less electronegative compared to bromine, and bromine is also less electronegative compared to chlorine, and chlorine is also less electronegative compared to fluorine. So the more electronegative the element is, the ease of release of the proton, because the electrons are pulled more towards that electronegative element. So it tends to form a complete ionic bond. So this is in order of increasing reactivity, and also it is also in increasing order of the acidity of the proton. So consider this reaction. What will be the final product? So you see that the final product will be the Markovnikov's product, and that will be this product. The Cl will be substituted here, and then the proton goes to this one. So let's show it by mechanism. So in terms of mechanism, this is our starting product, and then we have the HCl here. So this one we use is lone pairs of electrons to pick this proton, whilst the chlorine cleaves off. And when it cleaves off, we'll come to this intermediate with a plus here and then the proton here. So the chloride ion that was cleaved off will come and use its lone pairs, donate its lone pairs to this center to give us the final product. Sorry, so let me draw the final product here. The final product will look like this. Cl and then the proton. So let's consider this reaction. What will be the product formed when we add hydrogen iodide? So we are going to form the Markovnikov's product, which looks like this. So the chlorine will be here, and then a proton, a proton will come here. So this is the product that we are going to form. Now let's use mechanism to show it. So using this starting product, and then here's hydrogen iodide. So the lone pairs of electron, it will donate lone pairs of electron whilst cleaving of the iodine ion to give us the intermediate, which is a carbocation. So the plus is here, and then this one too is here, and then the proton is here. So I minus will come and donate its electrons here, and that will give us the final product, which is this product. Let's consider this reaction. What will be the final product for this reaction? Now, this reaction will lead us to forming the anti-Markovnikov's product. So instead of the Br going to the more substituted carbon, it will rather go to the less substituted carbon. So therefore, the product that will form will be this product. And then the proton will be somewhere here. So anytime you see HBr in a certain peroxide adding onto an unsymmetric alkene, then you are going to form the anti-Markovnikov's product. So let's consider this one too. HBr and hydrogen peroxide. What will be the final product? the final product will be the anti-Markovnikov's product, which will be this product. Now, let's show with reaction mechanism why it forms in this manner. The difference between the Markovnikov's product and the anti-Markovnikov's product in terms of their reaction is that the anti-Markovnikov's product follows a radical reaction. And in radical reactions, we have the initiation step. So in the initiation step, what happens is that the peroxide, in the presence of UV light, will cause a homolytic fission. And therefore, we are going to produce this radical, OH radical. So in the next step, which is the propagation step, what will happen is that this radical will come and attack the HBr. So it will form a bond with the HBr, which will cause the HBr to also cleave homolytically. So it will give us H2O, then plus the bromide radical. So it is this bromide radical that will go on to attack the carbon double bond. So let me continue from here. So using this, so we have bromide radical. Now there are two places it can attack it. So let me show this. So when the attack happens, we are going to get these two products. Possibility of getting these two products. We could get this one where Br is here, and then we have this radical on this tertiary carbon, or we could also have one in which Br is here, and then we have this radical on the primary carbon. Now, a radical on a tertiary carbon is more stable than a radical on a primary carbon. And therefore, here's Br. The reason why the reaction favors the anti-Markovnikov's product is that you see that with the anti-Markovnikov's product, the radical is created on the more substituted carbon. So in this case, this is a tertiary carbon, and then this is a primary carbon. A tertiary carbon radical is more stable than a primary carbon radical, and therefore the reaction will follow this order. So in the final step, what will happen is that we have a lot of HBr in the system. So let me write it here. So here is HBr. So together with this, it will also form another radical reaction, then throwing off a Br radical in the system. So we are going to get this. And then the proton will be here. So now, because it's a radical reaction, we need to talk about the termination step. I remember that in solution, we produce this radical, and then we also produce this radical. So what will happen is that in the termination step, the HO radical will combine with another OH radical to give us back the hydrogen peroxide again. Or an HO radical could also combine with this radical to give us this molecule. And then lastly, what could also happen is that there could be two radicals of this combining with each other. Sorry, there's a Br here. There's also a Br here. This molecule. Let's talk about the dichotomy between the Markovnikov's addition and the anti-Markovnikov's addition. The first thing is that in the Markovnikov's addition, you will need a protic acid. So it could be an HI, HCl, HBr, or even hydrogen fluoride. But in the anti-Markovnikov's addition, you need only hydrogen bromide in the presence of a peroxide. So, what we are really trying to say is that in the Markovnikov's addition, you don't need a peroxide for the reaction to happen. But in the anti-Markovnikov's addition, you need a peroxide for the reaction to happen. And then the second difference is that the Markovnikov's addition is an ionic. The reaction pathway is a ionic mechanism. It passes through ionic mechanism pathway. And then in the anti-Markovnikov's addition, it is a free radical mechanism. Then the last thing is that in the Markovnikov's addition, it can happen with either HI, HCl, HBr, even H2O. But in the anti-Markovnikov addition, it only happens with only hydrogen bromide. So therefore, anti-Markovnikov's addition is not a direct opposite of Markovnikov's addition because mainly their reaction pathways are different. Let's consider the reaction above. Let's use reaction mechanism to show the final product. So what will happen? In the first step, let me redraw the molecule. HBr is here. So there will be an attack by these lone pairs, causing the Br to cleave off. So we will form this intermediate. Sorry. So the proton is here, and then we will create a carbocation at this point. Now, will the Br attack this molecule at this point to give us this product? Now, this is not what will happen. The thing that will actually happen is that we see that this carbon is a tertiary carbon, and this carbon is a secondary carbon. So there is going to be what is called the hydride shift. If we shift this hydride to this point, you see that the carbocation will move from a secondary carbon to a tertiary carbon, which is much more stable than a secondary carbon. And therefore, this hydride shift will cause a move of the carbocation from being on this carbon to rather being on this carbon. So it is at this point that the Br minus will now attack that point to give this product. So in effect, this is the product that we are going to form from adding HBr. There is going to be a rearrangement reaction because the rearrangement reaction leads to stability. So let's consider this reaction too. You can pause the video and write the final product. But let's use mechanism to show the final product. So the HBr is here. This one will donate its lone pairs, causing the hydrogen to cleave off. When it cleaves off, we will get this intermediate. Sorry. So the proton is here. So this is the intermediate that we will get. But you see that this is a secondary carbon and this is a quaternary carbon. So in order to achieve stability, then what will happen is that instead of a hydride shift, Because if there is an hydral shift from here to here, we will rather move from a secondary carbon to a primary carbon, which is much, much worse compared to the secondary carbon. And therefore, instead of an hydral shift, there's rather going to be what? A methyl shift. So this methyl will shift to this point. And if there's a methyl shift, then it will move the carbonium to this carbon. So the bromine Br minus will bring its lone pairs to the side. And therefore, at the end of the day, we are going to form this molecule in solution. This is the molecule that will be formed from the bromination of this alkene. So therefore, the major product in this case is this product. Using mechanism, what will be the final product in this kind of reaction? You can pause the video and try. So this is the starting material. We have HBr in solution. So the lone pairs will attack the proton, causing the Br to cleave off. So we are going to form this kind of intermediate. And then there is a plus here. Now, which one will shift? Will there be a hydral shift or there will be a methyl shift? Now, let's look at what will happen in each of the possibilities. You see that this is a tertiary carbon, and this is a secondary carbocation, and this is a primary. Now, if there is a hydral shift from here to here, then the carbocation is moved on to a tertiary carbon. However, if there is a methyl shift from here to here, the carbocation is moved from a secondary carbon back to another secondary carbon. And therefore, instead of a methyl shift, there will rather be a hydral shift that will happen here. So this is what will happen to lead us into this product. See. Then the plus will move to this side. So in the final step, Br will donate its lone pairs and therefore will form this molecule. So this will be the molecule formed in the final step.